So the purpose of this video is to describe Lab 4 and really the derivation of the particle in a box. Well, not the derivation of the particle in a box. I'm sorry. To describe the to derive the formula that we get for which is E is equal to, I think, h squared n squared over 8 ma squared. Okay, where a is the length of the box, n is the energy level, h is Planck's constant, of course, and m is equal to the mass of the electron. So this is the energy. This is really cool stuff. So we're going to find that we get an energy which is equal to box, okay? But it's also equal to h nu, which is equal to hc over lambda. So we're going to get a bunch of lambda in this experiment, and we're going to liken it to the energy, and we're going to see how well it plays out into all of this. Of course, A, I think, is the factor that's difficult to appreciate, the length of the box. Now, the length of the box is something that I'll maybe do a separate video if you ask about that, or we may talk about that. But that's the, obviously n is the energy level. We're going to assume that the energy level for the first, we're going to be looking at the first energy level and the second energy level and so on. All right, so let me derive this equation here from what we know. Now, we know that the total energy operator times psi, the wave function, is equal to the energy times the wave function, right? And we also know that the total energy operator is h bar, it's minus h bar squared over 2m, second derivative, plus the velocity, right? That's the total energy operator. It's the Hamiltonian. Now we also know from the book that this goes to 0 because we're talking about a particle in a box, P-I-A-B, and we're interested on the inside of that, okay? And using, what the constraints of what we know a particle in a box to be, we find that psi is equal to some amplitude factor sine n pi x over a. That's just the wave function. You can look this up. This is given. Okay? This is also a given. Okay, so I'm starting here. With these two things, let's find out what the energy is. And we're going to find that it comes to that. And then we're going to say, wow, I love P-Chem when we're done with that. All right, so let's start out. This is a practice for your H psi, E psi. This is practice for your last exam. It's practice for your next exam. We're going to be using operators and getting eigenfunctions all the time. So let's do this, okay? H bar, it's minus h bar squared over 2m. Second derivative ddx of psi equals E of psi, right? Remember, I got rid of the zero. I got rid of the potential because it's particle in a box. Okay, this is then h bar squared 2m. I'm going to say d. I'm going to pull this ddx out because I want to do one derivative at a time, and now I'm going to put in this wave function here, a sine n pi x over a. And if I'm teaching this to a group of students in lab, as pre-lab, what I may say is, what should we do next? Right? That's what you're asking the students constantly. What should we do next? All right? Obviously, there's a couple things I can do here, but to keep things clean, I think I'm going to pull that a out and just rewrite this h squared a over 2m ddx sine n pi x over a. Okay? This is we're going to be bringing this all the way down and find out what that E is, right? That's the whole purpose of this, is to find out what that E is. The whole purpose is to derive this equation. Derive. You don't have to do this for the lab, but somebody ought to get up, if it's a professor or a fellow classmate, ought to get up and show that we could do this. This is something we are capable of doing. Okay, so what's the derivative of sine n pi x over a. And to keep things clean, I'm going to keep writing this part out, okay? But the derivative of this is just n pi over a cosine n pi x over a, right? Is equal to what? We'll keep going, okay? Now, let's pull this out to here because this is not a function of x, okay? So, x n pi over a over 2m, times a, right? Now, d dx cosine n pi x over a, right? The derivative of cosine of some factor times x is going to be, I'm going to write this first, n pi over a, capital A. But the derivative of this, now we're going to pull that part out. It's going to be, again, n pi a, right? And it's going to be minus sine of n pi x over a. Okay? Now let's go up to I'm running out of paper here, so let's go up there. Hopefully, I don't know if I was on screen when I did that, but I'm going to write this next thing out, and then I'm going to take these two factors, these two n pi over a factors, and combine them. Come over here. This is h bar 2m n squared pi squared over a squared. And there's a minus here too, right? So I'll go ahead and take care of that minus. Sine n pi x over a. Times a. We'll lost that factor, right? I'll put the a right here. And I'm going to go, wow, there's my psi, right? So this must be my e. You can see we're starting to get to something that looks like that, right? Except this looks just like h bar. This is h bar. So we now have to invoke this definition of h bar. That's equal to h over 2 pi. Okay, so now I'm going to say another form of h bar squared, which is h 2 pi times n squared pi squared over 2m a squared is equal to, right? This is still equal to e psi. I haven't been drawing that each time, but I pulled the psi out. This is now equal to e. This was equal to e psi, but I pulled the psi out because that's what we do with the eigenfunctions, right? Looks like a nice Chinese character. I'm not sure what it means, but it ought to be something special, like Pchem is cool. That's Chinese for Pchem is cool. Okay, so I'm going to rewrite this again. H squared over 2 squared pi squared times n squared pi squared over 2m a squared is equal to e. Looks like my pi's cancel, and this 2 becomes 4. 4 times 2 is 8, so it's h squared n squared, pi's cancel, over 8m a squared is equal to e. Wow. QED. That which was to have been demonstrated. That's it. Okay? So that's why we have this formula, which just goes in that's in your pre-lab right there. Yes, I admit. But I want you to derive it. I want you to see that, hey, that's something we could have figured out. Okay? And the only things we did to derive that were, we just invoked a couple things. Let me get a highlighter real quickly. This is going to take a second. Okay, we started with this. Okay, how did I get that? We started with that. Agreed? And with this. Those were the things that we assumed from the beginning. Why did we assume those? That would be a good open-ended test question at the end of an exam, like for extra credit, right? Why? Where did these come from? All right, and after that, all we did was just the math for this, and we found that we got this formula, which was given in your lab. All right, so again, a few definitions and so on. The length of the box, that's another good question to ask. Where do we get that? It's in your lab. If you read the pre-lab notes, you'll see where that comes from. Okay, this isn't everything, of course, that you'll need to understand for your lab, but it's sort of a good start. And if you decide to teach this to the class, then another student might get up and say, all right, let's talk about the A. What does A mean? Or all right, let's talk about N or the mass of the electron or whatever. Okay, hope this helps. Good luck.